Yo, that's good. Yeah, it's iPads on demand. Absolutely right. So the recording works. And now I need to share the screen, start broadcast. And that is the critical thing, I think. Start. Okay. So we should go over here. Now, can you see the screen? Brilliant. And keep everything crossable crossed that it doesn't crop out. But then, as I said, if push comes to shove, all I need to do is move over to the big computer. And if that doesn't work, because my wife is currently teaching and my kids are both doing online sessions, and I mean, our poor internet is just, but let's hope everything holds up and everything works all right. Yes, I fully agree with you, Edith. I fully agree with you, but I'm not telling you what part I agree with. And I could tell you a real story about Imodium, but this is a rather sad one, although it had a good outcome in the end. But where somebody actually tried to, well, kill themselves with an overdose of Imodium, and all you can think is, oh shit, and it doesn't work. But luckily, we managed to sort out that person. Yeah, oh damn, that's exactly what I thought at the time. But that's a long time ago, and I don't want to, yeah, not a good thing. And please don't, I need to give Bernardo his cue, and please don't forget to register on Moodle, which should be open.
No, like I actually really like Peter Clapper's lectures.
That's right, yeah. Do we actually still have the pizza fund? No, is it gone? What happened to it? Good. Okay, I tell you what, let's make a start. And very welcome to the second part of enzyme inhibitors. So what we have done in the session on, when was it? On Wednesday, I think. We started with enzyme inhibitors and we discussed basically the interesting case of reversible enzyme inhibitors, where the inhibitor can be reversed, the action of the inhibitor. Yep, absolutely. And I think people are desperate for some inhibitor jokes, so maybe we should come up with a prize for the best inhibitor joke, as judged by the panel. So anyway, what I showed you was if we've got our usual scheme enzyme plus substrate gives us an enzyme substrate complex, and this then is converted into enzyme plus product. We discussed the case of where the inhibitor binds exclusively to the free enzyme. So it would be basically binding to the enzyme here. And this would be the case of a competitive inhibitor. Now again, we have this reversible reaction and we form an enzyme inhibitor complex. We said that is a competitive inhibitor. Competitive inhibitor, because enzyme can only bind either the substrate or the inhibitor. So substrate and inhibitor are mutually exclusive. It's a little bit like Harry Potter and Lord Voldemort. There can be only one, or Highlander if you think about it. There can be only one, either the substrate or the inhibitor. If the substrate is bound, inhibitor can't bind. The inhibitor is bound, the substrate can't bind. And we said a competitive inhibitor can either block the active site, so that would be an active site inhibitor, and that is usually when the inhibitor looks similar to the substrate. Or it can also be an allosteric inhibitor. That is when the inhibitor binds somewhere else on the enzyme, but the binding of the inhibitor stops the substrate from getting access to the active site. And it's actually quite interesting how you find these inhibitors, because I told you the entire pharmaceutical industry is based on finding inhibitors. I don't know, maybe... What do you think about it? Or do you think it would be worth me doing a sort of an optional workshop in this enhancement week, in week 19, on drug design, how you find drugs? Would people be interested in that? Okay, then I'll see if I can schedule something. Monday or Tuesday, what's better for you guys? Well, actually, you don't have any lectures, do you, in week 19? On Tuesday. Let's see if I can do something on Tuesday. Okay, so this was the competitive inhibitor, and we said trademark of a competitive inhibitor that the Vmax in the case of a competitive inhibitor will stay constant. So Vmax with or without inhibitor is the same. We said Vmax over Km, how the substrate behaves at very low substrate concentration, how the enzyme behaves at very low substrate concentration. This goes down in the presence of the inhibitor. And Km, the affinity of the enzyme for the substrate, as a consequence, in the presence of the inhibitor, will go up. That means lower affinity for the substrate. And competitive inhibitor works best at low substrate concentrations. So low S. That is when the inhibitor is effective. At high substrate concentrations, the inhibitor doesn't work really. So that was the competitive inhibitor. I also showed you the case of the uncompetitive inhibitor. So again, the scheme, enzyme plus substrate gives an enzyme substrate complex. And here we've got enzyme plus product. And in the case of an uncompetitive inhibitor, this one cannot bind to the free enzyme. It can only bind to the enzyme substrate complex. And I indicate it like that. And again, because it is reversible, we have an enzyme substrate inhibitor complex. And this inhibitor is definitely an allosteric inhibitor because it does not bind to the active site. It binds somewhere else on the enzyme, and it can only bind to the enzyme when the substrate has bound first. So the substrate binds. There is then a conformational change in the enzyme, and this conformational change opens up a binding site for the inhibitor. And then the inhibitor can bind and stop the further process into producing the product. So uncompetitive inhibitors are always allosteric inhibitors. We said the trademark of an uncompetitive inhibitor is that Vmax definitely will go down. We said Vmax over Km. I see the comments. I see the comments that you are making, and I will reply to them in a minute. Vmax over Km stays the same. That is constant, with or without inhibitor. And Km, strangely enough, goes down. That means, apparently, the enzyme has a higher affinity for the substrate. It binds better to the substrate just simply because we remove this enzyme substrate complex. So we move everything in that direction, and therefore it looks like as if the enzyme has a higher affinity for the substrate. It likes it better, but actually it can't do anything because this way to generating the product is blocked. And can an enzyme have multiple sites for allosteric inhibitors? And the answer is absolutely yes. And we will come across a number of enzymes that actually have this feature, that they have several binding sites for different inhibitors. And why do we have these inhibitors? Why do enzymes have inhibitors? Well, we will discuss that in detail probably next week or the week after. The week after, I guess. But because enzymes are so powerful, we need to tightly regulate them. And the best way of regulating enzymes is through inhibitors. So that's why we need to know them. So this was the uncompetitive inhibitor. That's the uncompetitive case. And I think, Edith, you suggested on Wednesday, is it possible that we have a sort of a mixture? And that brings me to the main subject today. So let's say we have enzyme plus substrate. We have an enzyme substrate complex. We form product plus the enzyme. And now, what can of course happen, because life is never that easy, never black and white, where you just have either competitive or uncompetitive. You might have an inhibitor. Let's put it here. And this inhibitor can bind to both the enzyme the free enzyme, and it can also bind to the enzyme substrate complex. And let's call this inhibitor M, which, as you might guess, this stands for a mixed inhibitor. So this is the case of a mixed inhibitor. And again, we have the reversible case. So we have EIM and also ESIM. So this inhibitor can bind both to the free enzyme and the enzyme substrate complex. It looks like they are two different things here, two different inhibitor substances, but they are exactly the same thing. So the inhibitor can bind to the enzyme, to the free enzyme, but the same molecule could also bind to the enzyme substrate complex. Does that make sense? So the I stands for an inhibitor and the M stands for mixed. Okay, so we have obviously, absolutely right, we have obviously a mixture of the competitive and the uncompetitive side. So let me sort of color code that. That is the competitive component, and that would be the uncompetitive component. So here competitive component, and that here would be the uncompetitive component, right? So that is what we have. Now let's write again and let's try to figure out what happens to the enzyme parameters. So let's write down for the competitive inhibitor, we said Vmax stays constant, Vmax over Km goes down, Km goes up. For the uncompetitive, we said Vmax goes down, Vmax over Km stays constant, and Km goes down. Okay, so let's try to figure out how the mixed inhibitor actually works. And all we need to do is really, we need to sort of add these two, if you like, patterns together. And yes, you're pretty much right. It takes it. A mixed inhibitor has a competitive and an uncompetitive component in it, depending on how strongly it binds. So for some mixed inhibitors, the competitive component is much stronger than the uncompetitive component, and the inhibitor would look like pretty much like a competitive one, or the other way around. Now let's see what the mixed inhibitor properties are. So if we just add these two properties from the competitive side and the uncompetitive side together, what would you expect for Vmax in the mixed case? Does it go up, down, or stays the same? I think that's a very good, yeah. So Vmax still would decrease. We would definitely see a decrease in Vmax. Absolutely right. Because if we put them together, stays the same and goes down, net effect, it would go down. Absolutely right. Well done. What about Vmax over Km? Up, down, the same? Absolutely right. Vmax over Km would go down. What about Km? Km, up, down, the same. Kami, I love your thinking. It depends. Absolutely right. Km could still go up. This is when the competitive component is stronger than the uncompetitive component. Yeah? Because then it looks like a competitive inhibitor. Km could go down. We don't need to, because we said from just simply looking at these things, Vmax can only go down if we put them together. But for the Km, we sort of have opposing effects, whereas for Vmax and Vmax over Km, they are not really opposing. It's down or the same, and put together, it is down. So for Km, it goes down if the competitive component is smaller than the uncompetitive component. Does that make sense? So if competitive component is stronger, then Km goes up. If the competitive component is weaker than the uncompetitive, then Km goes down. What about the case of competitive component is exactly the same as the uncompetitive component? What happens to our Km in this case? Then it is the same. Then it stays the same. There is no effect, no difference, or it would stay constant. Km stays constant. If the competitive component is exactly the same as the uncompetitive component. Does that make sense? Do you think that happens very often, that these two components are exactly the same? Is that very likely? Does that happen? No, not really. I agree with you. It's not a terribly common case. But shall I tell you something? This is what you have been told in your A-levels, that this is, oh wow, that's a big thing, that Km stays constant. It is so, people think it's so amazing that it even has its own name. Yes, it's a scam. It has its own name. This particular inhibitor, where the unlikely case that the competitive and the uncompetitive component are exactly the same, has a name, and this is called a non-competitive inhibitor. And you've all heard this non-competitive inhibitor. It's touted as the, the big thing. So you were told in A-level, biology, oh, you've got the competitive and you've got the non-competitive inhibitor. Well, yes, you've got the competitive, but non-competitive inhibitor is really, a very, very special case of a mixed inhibitor. So non-competitive inhibitor Km stays the same, but the other parameters go down. But it really doesn't happen very often. Does that make sense? So instead of, I think, talking about non-competitive inhibitors, I would always prefer the phrase mixed inhibitor. Because I think there will always be some slight differences, and the inhibitor will be a little bit stronger binding to the free enzyme, or it might be a little bit stronger binding to the enzyme substrate complex. So I personally don't very much rate this term non-competitive inhibitor. Are you happy with this? So if we draw the Michaelis-Menten plots for the 3 inhibitor types that we've discussed, V over S. So in the case of, this is without the inhibitor. In the case of a competitive inhibitor, we have something like that. That's plus inhibitor, where the Vmax stays the same. And the the non-competitive inhibitor then binds both to the free enzyme and the enzyme substrate complex. It can stop the release of the product, like here, but it can also stop the binding of the substrate to the enzyme. So in the case of the competitive inhibitor, let me just quickly finish that. In the case of the competitive inhibitor, we have the same Vmax here in an Allosteric plot. In the case of the uncompetitive inhibitor, V over S, we have this without the inhibitor, and in the presence of the inhibitor, we have something like that. That's plus inhibitor. And you see, here we've got Vmax over Km. That stays the same. But obviously, Vmax here, these points will change. Okay? Now, in the case of that's the competitive, and that is the uncompetitive inhibitor. In the case of the mixed inhibitor, V versus S. So that is without inhibitor. And we might find something that looks like that. Right? So here that looks almost like a competitive inhibitor, but Vmax is gone down a little bit. So that's a mixed inhibitor with strong competitive component. And they are all, I only draw Allosteric plots. If we could also see something like that, V over S, that is without the inhibitor, and with the inhibitor, we might see something like that. So this would be the case of mixed with strong uncompetitive properties. Okay? So you see, it looks more like this uncompetitive inhibitor here, whereas this one here looks more like the competitive inhibitor. But they are not exactly the same then. And the third case, if they are both exactly the same, here we have without the inhibitor. And for the non-competitive case, where both components are exactly the same, we see something like that. That is plus inhibitor. And what you see is that the two lines here, the two gradients, are parallel, so they are the same. And of course, in this case, Km stays the same. So that is a mixed inhibitor with competitive component being the same as the uncompetitive component. Does that make sense? Brilliant. At least it makes sense to Michael. That's very good. Now, how do we actually find and how can we compare these inhibitors with each other? We must have some way of saying, oh, that's a strong inhibitor or that's not such a strong inhibitor. If we want to compare them, when we want to, find drugs, then, and I don't mean illegal ones, I mean bona fide drugs, painkiller or something like that. If you, for example, want to compare two inhibitors for an enzyme, you want to know which one is stronger. So how do we define stronger? Now, I alluded to that a little bit yesterday. So when I said we have the enzyme inhibitor complex, and this dissociates into enzyme plus inhibitor complex. And it boils down, you're absolutely right, higher binding affinity. But usually we look at the opposite. We are looking at how easy does the complex dissociate. So we are looking more at the dissociation of the enzyme inhibitor complex. And this is frequently called Ki, and in the case of a competitive inhibitor, it would be KIC. And that is defined as the concentration of the enzyme times the concentration of the competitive inhibitor divided by E the concentration of the inhibitor enzyme complex. So that's basically the dissociation constant. And the smaller the dissociation constant, the tighter the binding. Let me write that down. The smaller KIC, the better the binding of the inhibitor. The tighter, if you like, the tighter the binding of the inhibitor. So if we want to have a very potent inhibitor, we are looking for something that is called KIC, and we want this to be as low as possible. So how do we find that? Well, what we do is we do several enzyme reactions. So we take a substrate concentration and we measure the rate. So different substrate concentrations, we measure the rate, like we do without any inhibitor. And from that, we determine Vmax over Km, and we determine Km like we have done before with, for example, an Allosteric plot. And that is without the inhibitor. Next thing is we take a small amount of inhibitor plus inhibitor, and we do exactly the same thing. We take the substrate concentration in the presence of an inhibitor. Yes, there is. We do that, we determine the rate, and now we determine Vmax with inhibitor, and I indicated that we have got an inhibitor. We determine Vmax over Km with inhibitor, and we determine Km with inhibitor. And because it's so much fun, why don't we just simply add more inhibitor? Something like that. Let's indicate with these two pluses, we add more inhibitor. So substrate rate, we determine that, and so on. And we get our Vmax with even more inhibitor, Vmax over Km with even more inhibitor, and Km with even more inhibitor. Okay? And we can do, well, we can do a third one with even more inhibitor. And we get, for the different types of inhibitors, we get different values. So, for example, if, let's say, we have a competitive inhibitor, let's rewind. Competitive inhibitor does not change Vmax, right? So if we've got a competitive inhibitor, all our Vmax values would stay the same. So we would not see any difference, even if we use very high inhibitor concentrations, our Vmax would always stay the same. But our Vmax over Km would go down, would go even more down here, would go even more down in this case. And what we now then can do is, for a competitive inhibitor, we just simply plot the inhibitor concentration on the x-axis, and for a competitive inhibitor, we plot Km over Vmax. These are the values these values here that change these values. We take them and plot them against the inhibitor concentration. And what we find is something like that. We will get a straight line. That is for the competitive inhibitor. We plot Km over Vmax that we get for the different inhibitor concentrations, and we get a straight line. And this point here, and for the time being, just believe me that this is the case. I can do a video on the mathematical proof, but I'm not sure if you are really interested in it. This actually is negative, this point is negative KIC. This point here indicates the dissociation constant of the competitive inhibitor. So competitive inhibitor, we do Km over Vmax because that is what changes, Vmax over Km. In the case of an uncompetitive inhibitor, we do exactly the same thing. We plot the inhibitor on the x-axis, but we can't use Vmax over Km because for an uncompetitive one, for an uncompetitive inhibitor, Vmax over Km doesn't change. So for an uncompetitive inhibitor, we use 1 over Vmax. And again, we get a straight line. This point here gives us negative KIU. This is the dissociation constant for the uncompetitive inhibitor. And I do have videos on the playlist about these, how to find these KIU for these inhibitor constants, because these plots are usually done after you've done these plots here. So you have to find first, you have to find Vmax and all these parameters first. And then you can do these second plots. These are called secondary plots. Secondary plots. And it is the inhibitor concentration on the x-axis. Absolutely right. I should probably indicate it like that. These are called secondary plots. And they are also commonly known as Dixon plots. So these are the Dixon plots. So for competitive inhibitor, you plot Km over Vmax versus the inhibitor concentration. For an uncompetitive inhibitor, you plot 1 over Vmax versus the inhibitor concentration, and it gives you the dissociation constant. What do you do with a mixed inhibitor? What do you have to do with a mixed inhibitor? This is a very good question, Michael. This is because of the maths behind it. What do you do with a mixed inhibitor that has both? And what you can conclude from the Dixon plot is the dissociation constant. So for the competitive inhibitor, you can find this dissociation constant. For the uncompetitive inhibitor, let me write this down, we have ES uncompetitive. This gives us ES plus the uncompetitive inhibitor, and KIU is defined as enzyme substrate times inhibitor divided by the enzyme substrate inhibitor complex. So that's Ka. That's again the dissociation constant, and that is what we find out with these Dixon plots. How strong does the inhibitor actually hold together, or how easy is it to get the inhibitor off? Because if the inhibitor easily dissociates, then it's not a very strong inhibitor. Yeah, does that make sense? So these are the Dixon plots. What do you do with a mixed inhibitor where we have both components? Let's try to figure that out. If we have competitive, we do a purely competitive. We just plot Km over Vmax versus the inhibitor, and we get negative KIC. If we have an uncompetitive, all we need to do is inhibitor. This time we plot 1 over Vmax, get a straight line, we get minus negative KIU. If we have a mixed inhibitor, unfortunately, we have to do both of these plots. One for the competitive component, and one for the uncompetitive component. So we have to do both plots to get the contribution of the competitive component and the uncompetitive component. So for mixed, we have to do both Dixon plots. But if we know that we have a pure competitive inhibitor, we just do this one. And if we know that we just have a pure uncompetitive inhibitor, we just do this one. Easy. And both of these KIs tell us the dissociation constant. How easy does the inhibitor leave the enzyme to what it is bound? That is what KIs tell us. Right, we've done inhibitors, hey? Actually, I want to show you another inhibitor. Are you ready for that? It's Friday afternoon. We have 2 more inhibitors and we can do them in the next 5 minutes. Yeah, go on. Let's do it. Let me draw a Michaelis-Menten plot, because that is the easiest way to explain this inhibitor. We have rate, and let me write this nicely, substrate concentration. So we have our Scroll faster. We have our nice enzyme reaction, Michaelis-Menten plot, right? This is what it should be. Sometimes, and you will see that actually, sometimes you see something like that happening. Oh, wow. This is weird stuff. This is dark magic, isn't it? What is happening here? Try to interpret what you see here on the screen. We add substrate, reaction is reasonably fast, and then the more substrate we add, the slower the reaction becomes. What would you call this inhibitor? It's an oversaturation. I like that, yes. The substrate actually becomes an inhibitor. And this is called substrate inhibition. Substrate inhibition. It's not the enzyme, it's the substrate that is inhibiting. How do we have to envisage that? Okay, here's our little enzyme. Here we've got substrate. And that is, happening quite nicely. No, it's not feedback inhibition. But if we've got too much substrate, the substrate is blocking itself from getting access to the active site. So the active site is basically standing there like I do when my children fight and sort of let me know when you're finished. I can only deal with one at a time, but if there is too much substrate there, the substrate is blocking itself from gaining access. And therefore, we see a decrease in the rate. I think that's a very good explanation, Edith. The substrate is suffocating from the substrate. The enzyme is suffocating from the substrate. Absolutely right. So that is substrate inhibition. And you see that with a typical curve like that. I've got 2 more minutes for another inhibitor. Okay? Substrate plus enzyme. Oh no, we usually write it the other way around. Enzyme plus substrate gives us an enzyme substrate complex. And now I write it like that. Enzyme plus product. The substrate is the inhibitor in the substrate inhibition case. Now, we have said an inhibitor binds to the free enzyme, right? Competitive inhibitor binds to the free enzyme. That is what we said, right? Now, do you see in the way here in this equation, do you see something that can bind to the free enzyme? Of course, it's the substrate that can bind to the free enzyme. But can you see something else that can bind to the free enzyme? Yes, absolutely right. The product can bind to the free enzyme. And it could, in theory, drive this reaction backwards. So this means, how would you classify the product? What kind of inhibitor is the product? What kind of inhibitor? It is a competitive inhibitor. Exactly. The product, a product is always a competitive inhibitor. Because it can bind to the active site. That is where it came from. Bitor. That is where it came from. So a product is always a competitor. It competes with the substrate. And if we've got lots of product there, then the substrate can't bind because the reaction would go in the other direction. So product is always a competitive inhibitor. And that is the reason why we have to do the Michaelis-Menten reaction so that no product has been formed, because the product would inhibit the reaction. I hope you are suitably impressed. There's lots of stuff on the playlist. Have a look at it. And I think I've also put up some practice questions for you on this website. So have a go and see what you understand. And if you've got any problems, email me or put something in the group chat or something like that. But I hope you learn something about inhibitors. And I think I like this picture. If there are no burning questions, thank you very much for watching, and I hope you all have a magnificent weekend. Be good, don't do anything I wouldn't do, and enjoy the snow while it lasts. Thank you, and see you next week. Bye-bye.